We're going to continue on with Unit 5. We're going to talk about our last section, which is Learning Target 6F, all about inverses. By the end of this lesson, we will be able to find the domain and range for a function and its inverse, as well as find the inverse of a relation or a function as an equation. We will also be able to determine if the inverse will be a function or not using the horizontal line test. And lastly, we will be able to explain the connection between composition of functions and inverses. So we are going to start this lecture together in this video and then continue it in class tomorrow. So what is an inverse? Consider the relation f of x listed below. So as a review, a relation sends one input, so an x value, to an output that we are calling f of x here. So in this relation, -2 gets sent to 7, 0 gets sent to 3, 5 gets sent to -1, and 8 gets sent to 10. To find the inverse to any relation, we would switch all of the domain and the range values. Now for some notation, we call the inverse f inverse of x. And so this -1 that's up there in the, in the superscript, it's not technically an exponent. It is instead a notational convention that's used for naming the inverse. So the way we pronounce this is we say that this is f inverse of x. And again, that -1 is not an exponent. It is a notational convention for naming the inverse. Well, by definition, what the inverse is we are switching all of the domain and the range values. So if we had our original relation up above, where -2 gets sent to 7, as we flip the domain and the range, what that tells us for our inverse down here is that instead of sending -2 to 7, 7 would get sent to -2. Likewise, in the original relation, 0 went to -3, so -3 is going to 0 in the inverse. In the original relation, 5 is being sent to -1, so in our inverse then, -1 is being sent to 5. And for our last point in our relation, 8 was being sent to 10, so in the inverse, 10 is being sent to 8 instead. Two key takeaways here that are technically implied in the definition, but I want to make sure that they're very clear and that they stand out. The first is that the domain of f, so in our original relation right here, all of these x values was our domain of f. When we switch and we create the inverse, that becomes the range of f of x. So all of those values are now the range of our f inverse of x function. And likewise, our original range for our relation here, so our range of f of x becomes our domain values in the inverse. This connection between switching the domain and range values is what ultimately creates an inverse, but it's also going to be a huge concept later on when we start to talk about will our inverses still be functions or will we no longer get functions, and that's going to be the part of this lecture that we continue on together in class. Today during this video, what you guys are going to learn is how to computationally compute inverses. Now, before we jump into our first computational example, let's connect this back to what we were doing in our last section with composition of functions. So if we have f of x and f inverse of x, if they are indeed inverses, then another definition is that the composition of those two would have to produce the same output as we originally inputted. So what that means is that f composed with f inverse of x would have to give us our original input back. And if we compose them the other way and do f inverse composed with f of x, we should also get x back as well. And I want to use an example from up above so that we can see it. Let's take the first coordinate pair. So we're looking at the -2 going to 7, or the 7 going to -2 if we're looking at the inverse. Let's start by computing, and I think we'll fit it down below here. We'll start by computing f of f inverse. Now, since we're starting with this computation, our inside function is f inverse, so I need to pick some input that's from f inverse, so I'm going to pick 7. If we expand this out using our parenthesis definition, it would be f of f inverse of 7. Working from the inside out here, f inverse of 7 is going to 2, since in our inverse 7 gets sent to -2. So then f inverse of 7 will get replaced with that -2 value. Then from here, to find f of -2, well, we can use our original function f of x listed above, and we can see that -2 is getting sent back to 7, so f of -2 will give us back 7. What this is showing us is that our original input here of 7 is what we got back out after we composed a function and its inverse together. Now, for two relations to actually be inverses, we do actually have to make sure both compositions work out. So not only do we have to do f of f inverse, but we would also have to check f inverse of f. In this case, because we're starting with f as our innermost function, our input can no longer be 7 because 7 is not in the domain of f. Instead, we need to use that -2 as our input. Expanding this out, we had f inverse of f of -2. Working from the inside out, f inverse of -2 is equal to 7 based off of the relation that was defined for us. So we'll replace f of -2 with 7. Then from here, we need to find f inverse of 7, which we can see by definition is going to give us back -2. So again, although we started with a different input, whatever that input was, when we composed f inverse and f together, we got out that same input that we put into the composition. Now technically we would have to check this for all x values in the domain of both f inverse and f respectively, but this is just one example to help us see that when we compose two functions together and their inverses, we get back the original input that we had. And the reason that's happening is because inverses are undoing one another. Since we flip-flop the domain and the range, what's happening is we're ultimately picking something from the domain and it becomes the range of f of x, but then we're taking that value and that becomes the domain of f inverse, and then we input that into f inverse, which is giving us back our original domain that we had from f of x. Let's look at some computational examples here. So in our first example, it says use the relation f of x shown to the right to answer the following question. So our first question that we have is we need to list the domain of this relation f of x. So looking at the t-chart that was provided for us, our x values are 0, 1, 2, and 3, and our output values for those are 5, -2, 5, and 7 respectively. Now in this case, I don't have an equation, so our domain is not going to be a large set of numbers. It's instead just going to be the values that are listed here. So our domain is all of our inputs, so those would be our x values. So in this case, our domain is just the four values 0, 1, 2, and 3. The reason that I don't get anything else is because nothing else is listed in this table, and we don't have an equation that we are working with for this problem. Now our range values for f of x, that would be our output. So when I look at f of x, our outputs here are 5, -2, 5 again, and 7. So if I list each unique value once, we would get 5, -2, and 7 as our outputs. Our next follow-up question is a good review question from last semester. Is f of x a function? Explain. Why don't you guys pause the video right now and determine if f of x is a function or not. So as a reminder, to be a function, it means that every single input goes to its own output. So in this case, each one of my inputs is only used once, and they're each going to their own output. It doesn't matter that we're repeating stuff. What matters is that all of the x values here are unique, and they're going to some place. So yes, f of x is a function because every output only has one. Every input only has one output. Let's see if we can fit it there. Another way that we could determine a function is we could graph these points and plot these four values and use the vertical line test to see it. We could also use a mapping diagram to create it and make sure that every single one of our inputs only has one arrow coming out of it. Okay, in part D, we want to find f inverse of x. Well, to find f inverse, we just have a table of values, so we're going to create the same type of setup here for our f inverse. So we'll have our t-chart with f, or with x, and then with f inverse of x. Now to go from a relation to its inverse, we need to flip-flop the input and the output. So for our first coordinate pair here of 0, 5, instead of it being 0, 5, it would be 5, 0, since our input and our output are switching. For 1 and negative 2, our input will now become negative 2, our output will become 1. For 2 and 5, our input will become 5, and our output will be 2. And then for 3, 7, our input will now be 7, and our output will now be 3. So creating these when we have a t-chart, we are literally just flip-flopping the input and the output values. We do have to make sure that we're keeping them together though. So this 0 being sent to 5 is a coordinate pair of 0, 5. So when I flip-flop it, they still stay together as a pair. They wouldn't get mixed up with any of the other pairs on there. As some follow-up questions, we need to list the domain of f inverse as well as the range of f inverse. Why don't you guys pause the video here and list both the domain and the range for f inverse. So looking at our t-chart, to get the domain of f inverse, it's all of our x values, our inputs. So we have 5, negative 2, we have 5 again, but I only want to list each value once. So we just get 5, negative 2, and 7. For our range of f inverse, it's all of our outputs, which is going to be 0, 1, 2, and 3. And one thing I want to point out, going back to the concept of the domain of f of x equaling the range of f inverse, we can see that on here because our domain of f of x and our range of f inverse here, so part A and part F, are equal to the same values. Likewise, for our range of f and our domain of f inverse, I have the same list of values here for each one of those. And that's happening because by definition, the inverse is flip-flopping the input and the output. Okay, our last question on here for this relation is f inverse going to be a function? Explain. What do you guys think? Why don't you guys pause the video and determine if f inverse is going to be a function? So in this case, f inverse is not a function, and the issue here is that 5 as an input has 2 separate output values. So our issue here is that 5 goes to more than one place. 5 goes to both 0 as well as 2. And that's producing an issue because in a function, I need every input to go to one output. And here we have 5 going to both 0 and to 2. If we were to plot the points for f inverse here and plot these 4 points on a graph, we would notice that f inverse would not pass the vertical line test, and therefore that's why f inverse is not a function. We could also draw a mapping diagram and we would have 2 arrows coming out of the value for 5. Let's look at another example like this. So we have another relation given. This time we're going to call it g of x. It's shown to the right. We want to use it to answer the same follow-up questions. Why don't you guys pause the video right now and answer our first 3 questions here. So find the domain of g, the range of g, as well as determine if g is a function and explain. So let's check those first 3 together. Now our domain values is all of our inputs. So in this case, it would be 4, 8, 10, and 14. Our range is all of our outputs, which for g of x is going to be 0, 3, -9, and -5. Now to determine if g is a function, we have to make sure that every input goes to one output. So in this case, all of my inputs are unique, so yes, every input goes to one output. Our next part is going to be start to finding the inverse to this relation. Why don't you guys pause the video right now and write out what the t-chart would look like for the inverse of g of x. So find g inverse of x and organize it in a t-chart. So to find this, we're flip-flopping the input and the output. So instead of sending 4 to 0, 0 is being sent to 4. Instead of sending 8 to 3, 3 is being sent to 8. Instead of sending 10 to -9, -9 is being sent to 10. And for our last point on here, instead of sending 14 to -5, our inverse would send -5 to 14. So we have flip-flopped all of our input and output values, but made sure to still keep them as the same coordinate pair connection that they had coming from the original relation. Why don't you guys answer the 3 follow-up questions with the domain of G inverse, the range of G inverse, as well as determine if G inverse is a function or not, and explain. So to get the domain of G inverse, we're looking at what all the inputs are. So this would be 0, 3, -9, and -5. Again, another way to see that is that the range of G of x is always going to equal the domain of G inverse. To get the range of G inverse, we're looking at all the output values, which are 4, 8, 10, and 14, which matches up with exactly what we got up above for our domain of the original function. So since that inverse is flip-flopping the domain and the range, then our domain of our original will be our range of our inverse, and the range of the original will be the domain of the inverse. Now our last follow-up question on here is G inverse a function this time? And in this case, G inverse is actually going to be a function because every input has one output. So each one of these x values that's being inputted into G of x are each unique and they're being sent to one place. So every input has one output. Now this concept of determining if the inverse is a function is going to be a huge concept that we actually start talking about together in class tomorrow, but I wanted us to slowly introduce it and kind of see some examples where sometimes the inverse is a function, like down here in example 2, and sometimes like in example 1 up here, we got that the inverse was not a function. So I do have a follow-up question at the bottom of the page that says if f of x is a function. So in both of these cases, in both of these examples, f of x, the original relation in part 1 or in problem 1 was a function, as well as g of x, the original relation in example 2 here, those were both functions. And it's interesting to see that just because the original relation is indeed a function, the inverse sometimes is a function, like it was in example 2, and sometimes the inverse is not a function, like in example 1. So with our follow-up question of if f of x is a function, will the inverse be a function? Sometimes that happens, and sometimes it doesn't. And we're going to talk about, well, how can I really see if this is going to happen or not to be able to determine what's going on then. Now, our last set of examples that we're going to look at in this video together are going to compute an actual equation for an inverse. So in our first 2 examples of 1 and 2, we were just practicing with a small set of values off of a t-chart and computing their inverses by flip-flopping the x and the y coordinates. Well, the same thing's going to happen here. We're just going to generalize it to an equation. So to find an inverse equation, we have 3 things that we're going to do. We're going to need to switch the x and the y values. We're then going to need to solve for the y value. And then lastly, we want to replace that y value with f inverse of x, or if we're using g of x instead, g inverse of x maybe, because our question is actually asking us to find the inverse and not find y itself. So let's look at our first example. We're starting off with the equation f of x equals 8x plus 3. So my first step is to switch x and y's, but right now I technically do not have a y written, but I do have a y that's implied here. Remember, f of x is another name for y, so I could just rewrite this as y equals 8x plus 3 instead of f of x equals 8x plus 3. Now from here we can flip-flop the x and the y values. So we'll get x equals 8 times y plus 3. So there's our first step of switching the x and the y. And we do that because in an inverse, the domain and the range are switching, and our x here is representing the domain, and our y is representing the range. Now from here, we want to go ahead and solve for y, so we can subtract the 3 over and get x minus 3 equals 8y, and then our last step would be to divide through by 8 and get x minus 3 over 8 equals y. And since we were asked to find f inverse, we want to have our final step of replacing the y back with the function notation, which would be f inverse of x equals x minus 3 over 8. And also when I replaced it, I did flip-flop it so the f inverse was on the left, but technically we could have x minus 3 over 8 equals f inverse of x as well. Let's look at another example here. So in example 4, it says let g of x equal x plus 2 squared minus 10, and we want to find g inverse of x. So again, we're being asked to find an inverse. Our first step here is we need to create a y, so I'm going to replace g of x with y instead and get x plus 2 squared minus 10 all still stays the same. From here, our first step in really finding the inverse is flip-flopping the x and the y values. So I'll now have x equals y plus 2 whole quantity squared minus 10. So notice the structure of the equation still stays the same. I'm literally just flip-flopping the x and the y values, but the plus 2, the squared, and the minus 10 are all still there. From here, our goal is to solve for y. So one thing I definitely want to do is I want to add the 10 to the other side. So I'll get x plus 10 equals the y plus 2 squared. Now from here, I do have a couple options. I could FOIL out and distribute what y plus 2 squared equals and simplify that out or expand that out. But in doing so, I'm going to pick up a y squared, and I'm also going to pick up a single y term and more constant terms. Now if I were to try to isolate that, when I FOIL this out and distribute it, I would be creating both the y squared and the y term, which would be really hard to solve for two different places where I have a y. Instead, I actually want to leave this in factored form because I only have a y in one spot. And what we can do instead is I want to get rid of the square. So what could I do to both sides of the equation that would get rid of the square on the right side? Well, we could square root both sides of this equation. So last semester we learned that the square root and the square are undoing each other here. They're actually an example of inverse functions because they undo one another. And so we could apply the square root to get rid of the square, but that also means to keep the equation balanced, we have to apply it to the left-hand side as well. And lastly, we do need to add that plus or minus in front of the square root because we are applying that square root. From here, if we simplify stuff down a little bit, we get plus or minus the square root of x plus 10 equals, well, the square and the square root canceled, and we get y plus 2 on the right. The last thing to do from here is subtract and move to the other side. So we'll get negative 2 plus or minus the square root of x plus 10 equals our y value. So we've now solved for y, but because we were asked to find g inverse of x, we need to go ahead and replace that, and our final answer would read g inverse of x equals negative 2 plus or minus the square root of x plus 10. And that right there would be our final answer. Let's look at a few more examples together. So in example 5, we have h of x now equals the square root of x minus 4, and then outside the square root we have a plus 7, and we want to find the inverse to this equation. Why don't you guys pause the video here and start by setting this up. So set up what y would equal, and then flip-flop your x and your y values, and then let's check that together. So in our first couple steps, we've got to rewrite this as y equals instead. We still have the square root of x minus 4 and then the plus 7. From here, we got to flip-flop the x and the y values or switch them. So we get x now instead equals the square root of y minus 4 plus 7. From here, our next step is going to be to solve for that y value. And I want you guys to, again, pause the video. I want you to solve for this y value on your own first, and then we'll check it together. So to solve for our y value here, I'm going to start by moving the 7 over, which we're allowed to do because it's outside the square root. So we'll get x minus 7 equals the square root of y minus 4. Now from here, my goal is to get y by itself, so I need to get rid of this square root. Well, we're going to do the opposite to what we did in example 4. To get rid of a square root, I'm actually going to need to go ahead and square that, which means I need to go ahead and square the left side as well. And I want to make something very clear. We could not have done this in the first step because we still had that plus 7. So we instead first need to isolate the square root before we square both sides. And this was a skill that we learned last semester when we were working with solving radical equations. We always wanted to isolate that radical first and then apply the square to it to get it to cancel. Simplifying some stuff down, we get x minus 7 squared equals now y minus 4, because the square and the square root cancel. We could FOIL out the left-hand side, but there's really no need to. I would prefer to leave this unsimplified, mainly because it's going to give it to us in vertex form, and that's going to help us look at some graphs later on in class tomorrow. So from here, our last step is just to add the 4 over. So we get x minus 7 squared plus 4 equals y. And we were able to isolate and get y by itself. Last step, replace y with our notation for the inverse, which in this case is h inverse of x, since our original function was h of x. This would equal x minus 7 squared plus 4. And that will be our final inverse equation. Now let's look at one more example together in this video. So in our last example, we have k of x equals 27x cubed minus 1, and we want to find k inverse of x. Why don't you guys pause the video here and complete example 6 on your own first, and then we'll check it together. Alright, so to check this, our first step is going to be to replace that k of x with y instead, to get y equals 27x cubed minus 1. From here, we need to flip-flop the x and the y values, so we get x equals now 27y cubed minus 1. So flip-flopping that x and the y is inverting our domain and our range to create an inverse. And now from here, we got to start solving for y. So I can add the 1 over, get x plus 1 equals 27 times y cubed. From here, we can divide through by the 27 to get x plus 1 divided by 27 equals y cubed. Remember, both the x and the 1 are being divided because we're dividing each sides of the equation. Now from here, to get rid of the cubed, instead of applying a square root like we did up above in 4 to get rid of the square, we need to apply a cube root because the cube root and the cube would cancel. But whatever we do to one side, we have to do to the other side. In this case, since our index is odd here, with our 3 being our index and a cube root, we do not get a plus or minus. And so we end up with the cube root of x plus 1 over 27 equals our y value. Now we could simplify this a little bit. The cube root of 27 is actually a perfect cube. And when we have the cube root of a fraction, that is equal to the cube root of the numerator divided by the cube root of the denominator. And so in this case, we could simplify this to be the cube root of x plus 1 all over the cube root of 27 is equal to 3. And another way that we could also write this is to replace it with a 1/3 times our cube root of x plus 1. And then our last step is to replace that y with not f inverse, but k inverse, since our original function was called k. So we always just want to make sure we're paying attention to the original notation that we were given. And it's really easy to always just kind of write f inverse as we get in a habit, as I just did, but we want to make sure we're paying attention to whatever the original equation name was. We're going to continue on with this lecture in class tomorrow and talk about a lot of this stuff from more of a graph perspective and bring back the concepts of what's a function, what's not a function, and then learn how to expand that now to our inverses.